So today we'll start with a new concept of NP completeness. Basically, so far in algorithms, what we have done, we have attacked a problem and solved the problem in some polynomial time complexity. Now, naturally, there comes question like whether every problem in computer science which appears that can be solved with a polynomial time algorithm. The obvious answer is no. There are certain problems for which you cannot have a polynomial time algorithm. For example, you can have a problem where the output size itself is not polynomial. Suppose I ask you to enumerate all the permutations of n numbers, then you cannot solve it in polynomial time because the number of different permutation is n factorial, which is not polynomial at all in n. So not all problems can be solved in polynomial time, but there are certain other problems for which people don't even know whether that can be solved in polynomial time or not. There are still today, there are problems for which we do not know whether it can be solved in polynomial time or it cannot be. The answer is not known. So, but we can deduce certain facts about the problem, such as if problem A can be solved in polynomial time, then the problem B, C, D can be solved in polynomial time. So this is called the reduction. So this reduction allows you to classify the problems which can be solved if in polynomial time, if any one of them can be solved in polynomial time. And actually that class will constitute the NP complete class. Now to talk about it, I need to develop certain frameworks, certain tools. So that's what we will do first. So first is a problem. What do we mean by problem? That let us formalize first. So problem formalization. Now an abstract problem is a relation. What is the relation? It is I cross S, where I denotes set of problem instances and S denotes set of solutions. So an abstract problem is nothing but it's a relation between the instances of the problem and the corresponding solutions. So that is our abstract notion of problem. So like suppose you find the shortest path of in a graph, then the different graphs, given graphs will constitute one instance of the problem and the corresponding solution will be here. So the problem finding the shortest path between two vertices in a graph has different instances for different graphs. So that is the notion of instance. Instance of a problem is a particular graph in this case. Particular graph and given particular two vertices, the solution is also a particular solution. So that constitutes one instance of the problem. The problem itself constitutes all sets of graphs. That is the infinite set. So here is the example. Shortest path problem. For graph. So an instance is a weighted graph and a pair of vertices ST. A solution, so this is the instance. A solution is what? Is a sequence of vertices from S to T, from S to T, or a number that represents the length of the path. Number representing the length. So this is an instance, this is a solution, and that set of all this tuple, they constitute the problem. Now let us look at a specific type of problem which are called the decision problem. So in this case, the decision problem, the solutions are basically the decision whether it is yes or no. So I can ask, suppose for this particular example, in the shortest path problem, instead of given this only two vertices, I give two vertices and a number say k, and ask whether the shortest path between S and T has a length less than equal to k. This has a solution either yes or no. So this is the decision version of the problem. So a decision problem is an abstract problem with, now the solution set is basically yes or no. I am denoting yes as 1, no as 0. So S has 0 and 1 only. So the relation basically now is a function, is now a function. The function basically maps the instance to either 0 or 1. So the decision problem for the previous graph problem, decision problem version of the shortest path problem also specifies a number k and the solution is yes or 1 if L is less than equal to k, if and only if. So here is a remark. Typically, the decision problems are easier than its optimization version. So typically, decision problems are typically easier or at least not harder than the corresponding optimization problem. So if we prove that the certain decision problem is hard, then its corresponding optimization version of the problem is also hard. Like here the example, suppose here definitely the decision version of the problem is not harder than the optimization version. If there is a solution for the optimization version of the problem, that algorithm or that solution also can solve the decision version of the problem. How? What you can do, you first solve the optimization version of the problem. So basically you compute the length. Now you just check whether the length is less than equal to k or not. That's very easy. So in this specific example, the decision problem is lot easier than the optimization version of the problem. When you say easier, it means if there exists an algorithm for optimization version of the problem, that can possibly with a minor modification can also solve the decision version of the problem. So if we can prove or if we can show in some sense that the decision version of the problem is hard, then so is the optimization version of the problem. But it is much easier for us to handle the decision version of the problem because the solution set is only 0 and 1, and we will concentrate only on the decision problems from now on. Now of course this problem and these solutions inside the computer are represented as binary strings. So every problem, all the instances ultimately will be encoded as binary strings. So we will also encode all the problems in terms of strings of binary numbers. So you can, like for this graph problem, you can represent the graph and the given two vertices, everything encoded in terms of zeros and ones. So that's what we will do. And encoding is a map which goes from I, the instance, to the strings of binary numbers, zeros and ones. Now the strings of zeros and ones are represented sometimes as 0, 1 star. This means all possible strings with zeros and ones. This means that. So basically encoding is a function or a map which is taking an instance and encoding in terms of some binary string. That is the encoding. Now a concrete decision version or decision problem is a decision problem with I is basically equal to 0, 1 star. So your all instances are all the strings from 0 and 1. Certainly what it will happen if you consider all the strings from 0 and 1, some of the string will not represent the instance of the problem. Instance of the problem will be represented by certain strings of the zeros and ones. So what do we, when we say I is equal to everything, those ones which do not actually correspond to the problem, what we will assume for them the solution is 0. So I am going to write if a bit string does not correspond to a meaningful instance of the corresponding decision problem or abstract problem, sorry, corresponding abstract problem, then that string is mapped to 0. Now for the meaningful ones, either it goes to 1 or zeros, but the ones which are not meaningful in the encoding, we will map them to 0 basically. So this is the concrete decision problem. So a problem which is a decision problem and which has been encoded in terms of binary. That is the concrete. Now let me define, so now we have a notion of what is a decision problem when encoded in terms of binary. Everything we are looking at binary strings now. Now let me define what do we mean by this polynomial time. Let me give that definition now. First let me check how do we define now the problem. Problem Q is basically it takes an instance from 0, 1 star, that is the binary string representing the instance, and it maps to 0, 1. So this is a concrete problem, concrete decision problem. Now we say an algorithm solves Q in time Tn if for every I, which an instance of 0, 1 basically member of 0, 1 star. So I is an instance basically. The algorithm produces Qi, Q of I, in at most Tn time, where what is n? N is the length of the instance. So far we have known what is n? N is the size of the input. So in terms of this framework, n is nothing but the length of that instance, length of that binary string representing that instance I. So n is equal to the length of I. So the algorithm solves Q if it can solves Q in time Tn. If it can produce the solution Qi, Qi is the solution either 0 or 1. If it can produce Qi in Tn time, in at most Tn time. Now is the definition of polynomial time. If Tn is equal to order n to the power c for some constant c independent of n, constant means c independent of n, then Q is polynomial time solvable. We say that the algorithm solves Q in polynomial time, and if there exists one algorithm that solves the Q in polynomial time, then Q is polynomial time solvable. And polynomial time means Tn should be order n to the power c, where c is some constant independent of n. Now this gives us to classify all those problems which are polynomial time solvable. So let us define this. Say P, the class P is set of concrete decision problems that are polynomial time solvable. So all those problems which can be solved in polynomial time, they constitute the class called P. P is the polynomial time solvable problems. Sometimes people use some other notation, and I'll just tell you those notations so that you don't get confused. People say if Q belongs to P, that is polynomial time solvable, then people sometimes say Q is tractable. Otherwise, sometimes they say Q is intractable. But look at here, you need to know that Q does not belong to P to say that Q is intractable. Intractability does not mean that you cannot solve the problem, does not necessarily mean. It only says that it cannot be solved in polynomial time. So that's the notion. People sometimes they use these terms also, tractable and intractable. This tractability is with respect to the polynomial time solvability of the problem. Now let us see. Now we will formalize these problems a little bit more in terms of languages. This bit strings formed out of 0 and 1, if you take some subset of all the possible bit strings, this set forms a language. The language over the alphabet set 0 and 1. So let us see. So this is the formal language framework. So we are going to recast this entire problem solution scenario in terms of language. So a language, let me just first define what is a language. A language, for our purpose, is a set L which is a subset of this 0, 1 star. So language is nothing but if you take a subset of all the strings possible with 0, 1, they constitute a particular language. That's the definition of language. Now, consider an algorithm A and define the corresponding thing. And define as follows. A accepts a string x in 0, 1 star if ax equal to 1 and A rejects a string 0, 1 star if ax equal to 0. This is just a definition. I'll try to tell you what does all this mean. The language accepted by A is the set L such that it is a set of all strings in 0, 1 star for which x equal to 1. So that is the language accepted by the algorithm A. Now let me tell you what this language representing. The language is representing the problem itself. If you remember, the problem is nothing but set of instances and its solution. All the set of instances we have encoded with binary strings, and those instances constitute a language L. So now we are going to define an algorithm which basically we say that algorithm A solves the problem Q. It basically means the algorithm A for those strings for which the answer is yes should produce 1. So that is those strings A should accept, and for all the strings, for those strings for which the solution is 0, the algorithm should reject that string. Then we say that A solves that particular problem represented by that language. So a language corresponds to the instances. Language actually is representing the problem itself. And A basically the algorithm solving the problem if it does, as I said, for those instances it is the answer is 1, Ax should be 1. For those instances answer is 0, Ax should be 0. Now this definition here, A accepts and rejects, this is here the definition language accepted by A is a little bit more generalized version of this solving the problem by A. Why? Here you can see the language L we are saying that it is accepted by A only if x is equal to 1. But it is not saying anything what it will do when x does not belong to the language. So we are taking only those strings for which A is giving 1 and constituting the language L. We are saying L is accepted by A. But in this definition we are not saying anything what will happen if A is given the string x which is out of L. We are not saying anything about it. Okay, so if we say something about those ones also, then the definition changes a little bit. What it is said, then we say A decides the language L. We say L is decided by A if Ax is equal to 1 for x belongs to L and Ax is equal to 0 for x does not belong to L. Then we say A decides the language L. And as I said, look at this definition, two definition. A accepts the language L if Ax is equal to 1 for x belonging to L. This part is missing. Then we say A accepts L. We are not saying anything outside L what it will do. This distinction is very crucial. I'll tell you why. Let us take this problem. Suppose we are trying to solve or we are trying to design an algorithm which, given a program as input, so we are trying to develop an algorithm which accepts the set of programs as input and decides whether that program will halt or not on certain input. So we are trying to design an algorithm for which the input is a program and its input. So it should say, if that program halts on that input, it should say yes. If that program does not halt on that input, it should say no. And we already know that such an algorithm does not exist. This problem itself is not decidable. There is no algorithm A which can decide this language. You should make this distinction. This is a very subtle distinction. So there is no such algorithm which can decide whether, given a program and an input for that program, whether that program which will halt or not. But there exists an algorithm which can accept that problem. What does it mean? If the program on that input halts, then the algorithm will also halt. But it will not say anything if the program does not halt on that input. Your algorithm A also may not halt. But you will never know. It will go on, it will be going on computing, and you will never know whether it is going to halt or not. It can go on for millions of years, and after that it may stop. So the halting or not halting is a problem you will never know until it halts. So that's why this distinction is very crucial. Accepts and decides. Accepts means it halts only, but it will never say what it will do when the string does not belong to the language L. So the problem, the halting problem, the problem of what I just mentioned to you is called halting problem. It's very well-known problem in computer science, and this halting problem is not decidable. There does not exist any algorithm to decide on the problem, but the problem is acceptable by some algorithm due to this, according to this definition. So what is the algorithm you will do? The algorithm will be to run the program on that input. If it halts, you say yes. So that's your algorithm A. So this algorithm A accepts that problem because it halts whenever the program halts on the input. But if the program itself does not halt on the input, this algorithm will not halt. But you will never know whether it is going to halt or not. So you cannot say anything about those strings which are not there. So this is the halting problem, which is accepted but not decidable. Okay, now according to this definition, the class P is nothing but the language L, which is a subset of 0, 1 star, such that L is accepted by a polynomial time algorithm. So I am going to give a new definition of the class P, the polynomial time solvable problems. That problem, that class basically is those set of languages. Languages and problems are 1-to-1 correspondence there is. So this is a set of languages for which there is a polynomial time algorithm which accepts that language. But you can think over this proposition that if there exists a polynomial time algorithm that accepts a language, that necessarily decides also that language in polynomial time. So I am repeating this statement again. if for a problem or for a language L, there exists a polynomial time algorithm that accepts that language, it also decides that language. What is the argument for this? There is a very simple argument for it. You are saying it accepts the language in polynomial time. So there must be some bounded time, say n to the power c at most. So there is a time t less than equal to n to the power c in which the algorithm must accept it. So suppose it does not accept within that time, you can say that it has rejected the string. So you can decide also. But this is no more true if you don't say it is polynomial time acceptable. Because of the polynomial time acceptability, you can give a bound on the time for which you can run the algorithm. After that, you can say it has rejected the string. So polynomial time acceptance and decision are the same thing in this sense. So if, again I am repeating, if A accepts L in polynomial time, then this implies A decides L in polynomial time. Actually, it is in both directions. Obviously, this direction is obvious. If A decides L in polynomial time, definitely it is going to accept L in polynomial time. And this is also true. But this polynomial time is very important, otherwise I cannot make this statement. Otherwise, these two concepts are different. Now, let us look at a very specific problem which is called the Hamiltonian cycle problem. So, what is the Hamiltonian cycle problem? Why we are going to look at it is for to show you that to whether something is decidable or not, it is harder than some to verify the solution. So given a problem and a solution, it is easier to verify whether that solution is actually a solution of the problem or not than actually solving the decision problem. So let me first tell you what do we mean by this. So suppose we have been given the graph G VE, which is an undirected graph and unweighted. A Hamiltonian cycle is a cycle that contains each vertex exactly once. So suppose I draw this. This graph is a Hamiltonian, has a Hamiltonian cycle. Consider this cycle. This cycle has these four vertices exactly once. But let us see. This graph does not have a Hamiltonian cycle, because if you want to have all the vertices exactly once, you have to pass through this vertex at least twice. So it does not have a Hamiltonian cycle, but this graph has a Hamiltonian cycle. So a graph, now with this, a graph is Hamiltonian. A graph G is Hamiltonian if G has a Hamiltonian cycle. Now we are going to define the problem, the language for the problem. Corresponding language for the problem will be basically, so L is the encoding of all the graphs such that the graph G is Hamiltonian. So this is the language corresponding to this problem. We are asking whether given a graph is Hamiltonian or not. That's the problem. That's the decision version of the problem. And corresponding language is it's an encoding of all the graphs such that the graph is Hamiltonian. That is the language L. We are asking is this language L belongs to P. Whether this problem is polynomial time solvable. So in terms of the problem, we are asking whether given a graph is polynomial, given a graph whether it is Hamiltonian or not, that can be solved in polynomial time or not. That's the question we are asking here. Okay, this is one problem. On the other hand, look at the verification of the version of the problem. The verification of the version of the problem will be given the graph G and a cycle, verify whether that cycle is Hamiltonian cycle in the graph or not. And this is lot easier. You will just check whether it satisfies the property of the Hamiltonicity. So on the other hand, suppose Y is a Hamiltonian cycle in G, then we are considering this language. The language L prime, I am defining a new language which is an encoding of G and Y such that Y is a Hamiltonian cycle of G. So here is a new language L prime I am defining which takes the encoding of G and an encoding of Y, where Y is a Hamiltonian cycle of G. And then we are asking whether L prime belongs to P or not. So we are asking whether there is an algorithm given G and a Hamiltonian cycle of G, decide whether it is the Hamiltonian cycle of G. Definitely this is polynomial time solvable, because what you will do, given the cycle Y, you will check first all the vertices of the cycle Y is present in the graph G. Then you check all the edges of the cycle Y is present in the graph G. Then you check whether all the vertices of the graph G are covered. Then definitely Y is a Hamiltonian cycle of the graph G. And this entire thing can be done in polynomial time. So this version, verification, this is the verification. You are verifying a solution, whether actually Y is a Hamiltonian cycle of G or not. So this verification version is lot easier than the decision version of the problem again. So we will formalize this verification later again a little bit more in the next lecture, and from that one, from this verification we will see, we will define a new class of problems, new complexity class, as just like P we will define this new class as NP.